Hello guys, and welcome back to my channel Civil Constructor and Tutor, and this is the continuation to the video series of ETABS analysis. So previously we concluded our video with defining of section properties and material properties, and in this video we will continue with defining the load patterns, load cases, load combination, mass source and diaphragms. So let us continue, or let us start with load patterns. So basically I'll explain in the simplest term. Load patterns is the list of load that will be acting in your building. Okay, so we have two loads by default, that is dead load, that is the self weight of the structure, and for the type it is dead, self weight multiplier 1. So what does self weight multiplier mean? Self weight multiplier 1 and 0. It is simply, if you give 1, then it will consider the self weight of that structure or that element you have drawn in the model. For example, we will draw column, beam and slab. So that means it will take the self weight of the structure by default, but if we give a value 0, then it will not consider the self weight of the element. Then we have live load, which is the load that may be present or may not be present in the structure. Now let us list out the loading, and a proper visualization can be done through the architectural drawing. So we have wall load, okay, internal wall, external wall. Similarly we will have the parapet wall, okay, and a floor finish, and then we have earthquake load. So let us point out here. So external wall load, this is it is a dead load, yes or not, simply. And self weight multiplier 0, because we will give the load by ourselves, the structure, we are not going to draw the element, so it will not consider the self weight, we will give by our calculation. Add new load, internal wall load, add new load, this is also dead, and self weight multiplier will be 0. Floor finish on slab, this is also dead load. Then we have roof load, that is roof live load, so live, add new load. And we have earthquake load in x direction, this will be seismic. And we have two autolateral load, that is user coefficient, or we have a list of the autolateral load, and if you are using your own coefficient or by manual calculation, then you can use user coefficient, but for now I'll be using the Indian standard load, so IS 1893 2002 or IS 1893 2016. So for now I'll be using IS 1893 2016. Add new load. Similarly along y-axis, add new load. Any other load? Parapet wall, this is also dead, add new load. So these are the list of load that will be considered. Now we have to modify EQX and EQY, okay, and for this go to modify lateral load, and for x-axis uncheck all of this and check all in x direction, that is x direction plus eccentricity, x direction minus eccentricity. And it is not necessary to tick this because it will consider automatically. So okay, eccentricity ratio, this is 0.05, okay, and story range base to story 4. So this is the story range. For this I have a simple PDF over here. So our building is without basement on level site, So for typical building on level site with competent swell, the base is generally close to grade. For a building without a basement, the base is generally established near the ground level slab elevation. So base level is at ground floor. Okay, we will not consider the plinth level, or sorry, we will not consider from the foundation level. So that means we will consider our building responsible for seismic movement from the base at ground floor, because this portion is within the structure and there will be no any significant motion of this portion. So base and up to story 4, is that okay? So let me show you in the architectural drawing also. So we'll consider our building or the seismic height from this level 1 2 3 4. So this is base, story 1, story 2, story 3 and story 4. So with a basement, then we have to consider the basement level as well. Response reduction factor 5, because this is SMRF building, that is special moment resisting frame. This is also from our code. Let me show you. So in IS 1893 part 1 2016, response reduction factor for building with special moment resisting frame, that is ductile detailing, will take as 5, and for OMRF, that is without ductile detailing, it is taken as 3. So 5. And seismic zone factor, our Nepal lies in zone 5, so it is 0.36. Soil type medium soil, so 2. An importance factor for a residential building is taken as 1. For apartment it may be taken as 1.2. For hospital it is taken as 1.5. okay. And time period, so here we have 3 options: approximate, program calculated, user defined. So program calculated is by default, the program calculates the time period. Approximate, it will take the constant 0.075. so this is also from the code. Let me show you. So it is in clause, okay, so 7.6.2, the approximate fundamental translation natural time period is taken for bare MRF building, that is without any masonry infills. So MRF, moment resisting frame buildings, we have 3 values: time period 0.075, s to the power 0.75, that is RC MRF building, which is our case. It is a simply reinforced concrete moment resisting frame building. So time period is calculated as 0.075 s to the power 0.75. So approximate 0.075, or you can directly go to, so this is the constant, okay, 0.075, or you can also go with the 0.080 depending upon your building type, but for now it is 0.075, so I will not change. Or you can also put it by user defined, that is 0.075 into height of building, so 3 meter 6 9 12, so 12 to the power 0.75. so this is our time period 0.483. Either you can go with this option or you can go with approximate, keeping the constant as 0.075. okay. Similarly for EQY, untick all x direction and tick out the check for y direction plus eccentricity minus eccentricity. Other things will be same, that is 5, and go to approximate. There is no any difference for approximate and user defined because we are taking as 0.075. okay. So load pattern defining has been done. I hope you are clear up to here. Okay, now we'll check for load cases. So the load cases has been automatically defined. If we click for edit option or modify option, you can see here simply a load case it defines how the load patterns are applied either statically or dynamically, and how the structure responds linearly or non-linearly, and how analysis is performed through model analysis or direct integration. So this is the purpose of defining load case. Okay, so load cases has been defined. Now for load combination, so either you can use your default load combination or you can make your load combination by adding it manually. So I'll show you load combination. So dead load plus live load, it may be a load combination. Similarly, 1.5 times of dead load plus live load, that may be another type of load combination. Similarly, 1.5 times of dead load plus 1.5 times of live load plus minus 1.2 times of earthquake load. Okay, this is how you will take the load combination. But we are using IS code, so we have a default load combination for concrete designing. So concrete, check for concrete frame design, and okay, so we have got the load combination. Now if we see here, it says 1.5 times of dead load, these all are dead loads. Yes, so it is 1.5 times of dead load. Similarly, decon 2, it consists of live load and dead load with a scale factor of 1.5, and D3 has earthquake load as well, so 1.2, and decon 4 has minus 1.2 earthquake load. In the last okay, decon 14, and in the last four load combination we will have 0.9 times of dead load and 1.5 times of the earthquake load, that is the lateral load. So here you can see that the scale factor has come to 0.9, which was 1.5 or 1.2 previously. So basically the combination of 0.9 times of dead load plus 1.5 times of the lateral load is done in order to consider the body being light, and it will be much more easier to overturn the structure in response to the earthquake loading. So we are taking 0.9 times of dead load. Suppose the earthquake is causing an anti-clockwise moment, then the dead load opposes, obviously the dead load is responsible for opposing the moment and conceived by a clockwise moment. Then the dead load being actually reduced, then the earthquake effect being scaled with a higher value, then it will try to overturn the building. So we are considering the most severe case to check the stability of the building. So in a simple term we can say that the anti-clockwise moment is being scaled by 1.5 times, and the clockwise moment, which is the resisting moment, is being scaled by 0.9 times, which simply means reducing the clockwise moment, that is the resisting moment. So we are done with the load patterns defining, load cases defining, and the load combination. Now let us come to mass source. We have to define mass source. What is mass source then? We have defined load patterns, we have defined load cases, we have defined load combination. What is mass source then? So in simple terms, mass source considers of all the masses that involves or that induces the seismic loading or seismic load of the building. For example, consider a water tank. It will have water in it. During the earthquake, the mass which will involve in the seismic motion will be the summation of the water tank as well as the water contained within it. Okay, so that will be the total mass that will be taking part in the seismic motion. So similarly in building also, the mass that will involve in the seismic motion has to be considered in the mass source. So modify mass source. Mass source name, mass source 1, you can give any name, let us keep it as mass source 1. And element self mass, additional mass, specified load patterns, adjust. So these are the point I will discuss now. Element self mass. Before that I will take this specified load patterns. I will specify the load patterns or the list of load. So now the next thing we'll define is mass source. So what is mass source? Let me keep it simple. Okay, So mass of the structure, that is including self weight, additional mass due to the surface load, usually dead load and live load. So these all sum up to the seismic mass, that is the mass of the building which excites during the seismic motion. For example, a water tank containing water. When there is a seismic motion, the water tank as well as the water within the water tank get the excitation during the motion. So that means the water as well as the water tank is the total mass that is uh, taking part in the seismic motion. So we have to include the load which will be a part of the earthquake excitation. So this is simply mass source. Now modify our show mass source. I will tick specified load patterns and then I will explain other things. Okay. uh, Dead load add, and external wall load. I will add dead load only. Internal wall and floor finish, which is also dead load, and parapet wall, that is also dead load. Now for live load, we come to table 10 in the IS 1893 part 1 2016. So if the dead load is up to 3 kilonewton meter per meter 3 kilonewton per meter square, then the percentage of imposed load is taken as 25, and above 3 kilonewton per meter square it is taken as 50% of the imposed load. So this is the point we have to understand. And for general loading in the residential building, we should know the value of loading. For example, the live load taken for balcony, veranda, corridors, cantilever projection, it is taken as 3 kilonewton per meter square, and for a staircase it is taken as 3 kilonewton per meter square. So that means we will have to take multiplier as 25, okay, percentage of imposed load. So for now there is a cantilever projection, there is staircase, multiplier will be 0.25. Similarly for roof loading, whatever the value for roof load or whatever the value of live load in the roof will be, the multiplier will be 25% only, because due to the chances, okay, it is the probability of the live load being present at the roof during the earthquake. It may be not, the probability may be very less that the live load will be present in the roof during the earthquake. So we'll take as 25% only. So why mass source has to be considered? So basically it is required for calculating the base shear of structure and performing structural analysis, okay, or seismic analysis. So we'll consider mass source. Now we have to untick element self mass because we have already considered dead load. So by specifying load patterns we have to uncheck element self mass, okay, and the lateral mass will be lumped at the story levels. So by checking this box, all the assigned translational mass in global x and y direction and assigned rotation mass about the global z axis will be lumped together for a given story level. So basically it means that all the mass are lumped or are accumulated at the story level. The z component being smaller, so we do not include vertical mass. Include lateral mass ensures that the mass along x and y direction are included. No, what is the edit that I have made? Okay, a roof load 0.25 add. Okay, so another task is to assign diaphragm. So basically diaphragm are the horizontal structural elements with two primary roles. The very first being to resist and transmit various types of load, and the other is to tie the vertical elements firmly. You can also find in the code that a diaphragm is a horizontal or nearly horizontal structural system, for example reinforced concrete floors or horizontal bracing system, which transmits the lateral forces to vertical elements connected to it. I hope you are clear about the function of diaphragm. Now let us assign diaphragm to our building. And So modify also diaphragm, and here you can see two types of rigidity. One is rigid and another is semi-rigid. Basically, rigid diaphragm is assigned when the horizontal structure does not deform itself considering the lateral load. And for the semi-rigid, it should be modeled when significant in-plane deformation occurs, taking into the account of the respective stiffness of the diaphragm. So basically, a semi-rigid option will be selected or will be undertaken when there is to be done a more detailed analysis, when the number of modes is higher in the building considering the eccentricity in building. So that may be option for the semi-rigid. And there is also another type of rigidity, that is a flexible diaphragm, and it is considered when the average deflection at the midpoint exceeds the twice average deflection at the corner points. So for defining the diaphragm, either you can define one level, that is D1, and assign it to different floor levels, as ETABS will automatically assign the different diaphragm system, or you can label diaphragm for each floor respectively. So here you can see, okay, add new diaphragm, okay, add new diaphragm, okay, add new diaphragm, okay, as we have 4 different floors. So I will be assigning 4 number of diaphragm. So this much in this video, and in the next video we'll continue with the modeling of the structural elements of our building. Thank you. Do like and subscribe.